Good morning. I totally opened the wrong file. Or I guess afternoon or whatever time you're watching this. So today I thought we'd think about what is a dream or a goal of yours. So just take a minute, pick something. It doesn't have to be big, it can be small, but I think it's important for us to always have these. Anyhow, if you guys have questions, let me know. Today what we're talking about is volume of constant cross sections. So this was definitely something that kind of was difficult for me first visualizing it. So what it is we start with some arbitrary area, right? Here's our f of x, here's our g of x. And we want to take this area and then imagine turning it on its side. So this is going to be the base of our shape. Okay, so if you were to look at it like from the bottom, this is the shape that you would see from the bottom. Okay, and so that's kind of an important piece is when we're looking at it on our graph, I should use my highlighter. When we're looking at it on our graph, then we are looking at essentially the bottom of this like figure that we're working with. And it's a three-dimensional solid, I guess, more so than a figure. So this would be what the bottom shape of it is, okay? The way we turn it into a volume is we decide that we are going to fill this shape with something that sticks straight up out of it. So this is standing up. And it's sticking straight up in the air at me, so that's why it looks like just a little line because I'm looking straight down at the top. So if I were to turn this sideways, I have this weird little shape and thing, and then I have these things that stick up out of it. Now, whatever shape it is, they'll tell us, and it's generally, perpendicular to the x-axis. That means we're going to be using dx. Should they torture us with something that's perpendicular to the y-axis, we're going to need to use dy. But in general, they don't do that. It's hard enough. They'll also tell us some information. They have to tell us what shape this is. So often one that we do is we do squares, okay? So if a square is sticking up out of this, what's important for us to think, sort of our first logic leap here, is this little square, see the thickness of the square, that's dx, and then this is the square from the side, so I don't really see it here either. But the important thing to think about the square is this side is like here, and then I'm going to call this one y here, but if it's a square, these two are the same, so my area is just going to be x squared. So let's maybe change this back to x because that would be a little more appropriate since those two are the same size. So this height is also x in the case of a square. Once we have the area of our little cross section, right? So we cut it out and it's a cross section that's some changing size but same shape. Once we have the area of a cross section, we of course turn that into a volume by accounting for its thickness, which is dx, and then we integrate our area function times dx, which gives us the total volume, right? Because if we add up all those little volumes as we move along this shape, as we add up all those little volumes, that's going to give us the total volume. So let's try a couple problems and see if that helps. And then reach out if you guys have questions or any thoughts on this. So here's our idea. Oh, I should have made pictures, but I guess I'll have to just make them here. So it says find the volume of a solid with base bounded by these lines. And so this is f of x equals 1 minus x over 2, which I know is actually just a line with a positive intercept and a negative slope. So I'm going to draw something like this, right? When x is 0, we get y equals 1. This is f of x. 0, y equals 1. And g of x is negative 1 plus x over 2. So g of x is actually kind of a similar shape, right? But it's reflected across here. This is g of x. And this intercept is at 0, negative 1. Both of them intersect over here at 2, 0. And then, of course, our other boundary it set up there was the line x equals 0. So a couple of things I know are tricky. Ooh, let me hide that. A couple of things that I know are tricky are, first of all, determining what it is that is sort of the area that we're dealing with. So our clue there is the bounded by. So the bounded by is the same as saying trapped, right? Boundaries trap you. So this is trapped by these lines, right? And so we just take our graph and we say, okay, what is like enclosed by those three functions that they gave us? I don't know why my thing hates me, but the scrolliness is not working. There we go. So in here is what's trapped by the three functions that they gave us, f of x, g of x, and that x equals 0. Okay, so that's our first part, is just where is this area? So that bounded by helps us. Then it tells us, so I'm going to switch back to a regular pen. Then it tells us that we are dealing with cross sections that are perpendicular to the x-axis. So they're going like so, right? Perpendicular to the x-axis. And they are squares. And so that means that this little thing, if I were to pop it out, it's a square that's sticking straight up out of this thing. So as I go down, like down here, my squares are very tiny. Here, my squares are the biggest they can be. So this distance right here is my side length of my square. Maybe I won't call it x. Let's call it L for length, because I don't like to use S because my S's look like pies. So we'll call it L for the length. I know that the area of my square is just L squared. But can I find this height, L? You guys are like, of course we can. That's just a top minus bottom situation. So L is the top, which is f of x, minus the bottom, which is g of x. Now, L's not constant, right? L's big over here and L's small over here. So that makes sense. So L is, let's see, f of x I said was 1 minus x over 2. Minus, and g of x I believe was negative 1 plus x over 2. And then let's go ahead and simplify that just a little bit, just because it's kind of ugly. 1 minus x over 2 plus 1 minus x over 2. So this is nice because it comes out to be 2 minus 2x over 2, which is really just L equals 2 minus x. Everybody follow that algebra. So what I'm saying is this distance here is 2 minus x, which turns into this side of my square is 2 minus x, but this little guy is a square, which means both sides are the same, all sides are the same. And so then the area of my square is going to be that 2 minus x squared. I turn it into a volume using dx. Okay, now this expression right here, this 2 minus x squared dx, that's basically like the volume of one tiny little infinitesimally narrow square that's sticking up out of there. So I need to accumulate them all. And so I need to start back here when x equals 0 and stop over here when x equals 2. So those are the bounds of my limits of integration. And then once we're here, I have faith in you guys being able to work this the rest of the way out. From an integration perspective, to be totally honest, we don't have to expand it out if we don't want to. It's about the same either way, I think. But if you think about it from like a u sub perspective, I don't know why my pen is that. Sometimes u would be 2 minus x, right? Then du would be negative dx. So you could totally solve this with a u sub. Personally, I think it's easier just to go ahead and integrate this out. Every once in a while, people are confused as to why we don't have a pi here. The reason why we don't have a pi is because we aren't dealing with any sort of circular volume. And so we don't need a pi to write the function for our volume. So we integrate this and we get, let's see, that's 2x squared, and then that's x cubed over 3, evaluated from 0 to 2. Remember, I do want you to show plugging in. You don't have to show all of the little tiny pieces of the evaluation, but I do want you to show plugging in. And this is 4 times 0 minus 2 times 0 squared plus 0 cubed over 3. Meaning I want you to show plugging in the 0. It's fine for you to say that's all going to 0 afterwards. And then let's see, this looks like we have 8 minus 8, which is just going to give us 8/3 for our total volume. All right, let me know if you guys have questions on that. See if I pulled one of my things like I did on Tuesday and made a mistake. So it's just a new way of thinking about how we might have a volume, but not necessarily in new calculus today. So a little bit of a brain stretch, but not necessarily new calculus. Let's try another example. All right, so this one is the same graph. So I'm just going to draw a graph real quick. Here's our f of x. Here's our g of x. And then here's our x equals 0 line. So we see that those graphs that we drew, they are trapping this triangular area. So that's our base, okay? And then this time, same idea. We are still moving perpendicular to the x-axis, okay? So still perpendicular to the x-axis, but this time they're semicircles. So this distance, which we can call L again, that distance L is the base of my semicircle, which is a little bit tricky because I have to be careful, because that means that my radius that I want is only half of L. Do you see how L is going to be the diameter of our semicircle? Because the semicircle is sitting on top of this area. So it's like little, if I were to look at it from the side, I would see this. And then if it were coming toward me, you can imagine it would be getting like narrower and narrower. Just pretend that, say it were sitting on its side, like, but I turned this, so I lifted this corner, whoop, so it's like flat, right? You would see this going back, and then, oh, I don't know, this would look like a dome, but I don't think I can draw that very well. That's really boring, because it's gonna look like this, but this would be like rounded, because they're like semicircles, but I'm not sure that my art is very good. So I guess the big leap that I'm saying is the important thing is this distance across is my diameter and not the radius. Because the area of a semicircle is half of pi r squared. Now, I found L a minute ago because we were using the same area, right? And so that distance across we found was f minus g, which we simplified to be 2 minus x. So L is our f of x minus our g of x, which, like I said, that is our 2 minus x. So R is going to be L over 2. You follow that? So that our area is going to be 1/2 times pi 2 minus x over 2 squared. Caution right here. Oh, my pen didn't change to red. How tragic. The caution right here is when you square, make sure you square the top and the bottom. That's not going to be over 2. It's going to end up being over 4, which is the most common mistake that we tend to make. So that our total area is pi over 8. 2, 4, 8, times 2 minus x squared, which then means our volume is the integral from 0 to 2 again. That pi over 8 can move out in front, right? It's just a coefficient, 2 minus x squared dx. Remember, the pi over 8 showed up because we're dealing with semicircles. So at this point, our integral is the same as what we did before. So I would say at this point, just use your calculator. Do you guys all remember how to do our calculators? To evaluate it, but if we didn't evaluate it, that's actually this one's really easy because see how we did this integral 0 to 2 of 2 minus x squared dx, and we found that that was 8 over 3. So since we've already done this integral right here on the earlier page, from 0 to 2 of 2 minus x squared was 8 over 3 from number 1, we can see that this answer is going to be pi over 8 times 8 over 3, and you're going to get pi over 3 for your final answer. You can check that in your calculator and let me know if that doesn't make sense. Some of those arithmetic shortcuts we took there. Okay, so really what it is the only thing that was different is we changed the shape, and so you had to find the area of a different shape. So that's really the most torturous things we can do to you is change the shape. So this one, we have equilateral triangles. Now, equilateral triangles, we have to really think about a little bit. They kind of do weird things. And at first, your instinct is like, I don't know that we can find the area of an equilateral triangle if we only know the base, right? Because that's what's going on. Oops, I forgot I need my highlighter. That's what's going on here is we have this little guy, and then we are putting in, here's my L, equilateral triangles, and they have a base of L. So there's a really convenient formula. I don't know if any of you have ever heard of it, 1/2 AC sine of the angle in between, but we don't need to necessarily go down that road. But that is a lovely formula. We can see where that formula came from pretty easily by thinking about dropping this. This is nice because if I drew my picture better and I actually had an equilateral triangle and not a wonky triangle, this is going to cut our base in half because I cut my angle in half, and because this side was the same and this side was the same, and then these angles are the same, and then these angles have to be the same. Pretty sure you were supposed to prove this in math too. Anyhow, cuts this in half. Which is nice because we can find this side because we know this angle is 60 degrees and we can use SOHCAHTOA, which is where this whole formula comes into play. So this formula works for all triangles, not just equilateral triangles. But anyhow, if we use SOHCAHTOA, if I pop that little triangle out, this is 60 degrees. This is L over 2, whatever half of my base is. And this is the height that I would like to find because you guys know area of a triangle is 1/2 base times height. That's the one we always learn. This is one that you learn if you spend, like, I don't know, a lot of time in geometry or maybe take IB classes. That was what I taught it. But anyhow, come over here. SOHCAHTOA says, oh, we also know this side is L. SOHCAHTOA says that if we want the height is equal to, height is my opposite. So height over L is equal to the sine of 60. Follow that. So then I just get my height is equal to L times the sine of 60. And you guys know sine of 60 because 60 is pi over 3, right? And sines are y, so it's the bigger one. So this is square root 3 over 2 times L. Base was L, height was square root of 3 over 2 times L. So 1/2 is our area. L is still this distance across the base, so L is still our top minus bottom, or F minus G. Then the important thing is realizing that L is the base of the equilateral triangle, and the area of that equilateral triangle in terms of L is this. Feels a little related right to like from that in terms of other things. We found L to be the 2 minus x. And so we get our area is, I'm going to move that to root 3 over 4, 2 minus x squared. So we get our volume to be the integral from 0 to 2. We can move that root 3 over 4 out. 2 minus x squared dx. We found this integral earlier. 3 over 4, oh gosh, what was it? 8 over 3, I think. Yep. 8 over 3. The 4 reduces with the 8, so we get 2 root 3 over, I guess, not 6, but 3 numbers. I do much better if I don't just reduce in my head and I reduce out like this. And then I don't make so many mistakes. So we were able to take a shortcut here just because we had solved it in A, but we wouldn't usually show that. We would show our work. So let me know if you guys have questions. Hopefully that helps. I forgot to put in my little pause my video here slides, mostly because this one I felt like was really weird to set up. So that's why we didn't do the pause the videos, because I really struggled to visualize these as a student. So maybe, hopefully I did a better job. All right, so today for your homework, you're gonna go into Schoology and the problem set should be there. I think there's 10 questions. There's a few like this. It's just area and then volume. So we have both the rotated around X. I think it's mostly, I'm not sure. I can't remember if I have any around Y or not. Like the Y-axis type. And then definitely we have these constant cross sections is what they're called. All right, have a good day. Let me know if you have questions and we will talk soon.